So, we've done a few things with graphs. We've talked about like how you can just read information off from them. Especially if you have access to a computer and just get a computer-generated graph, you can use that for lots of things. You can look at a graph and just answer, is this thing even or odd? What are the maximum values? Where about does it look like it's increasing or decreasing? But if you want to do things by hand with that starting point, well, you just need to know what some graphs look like. So that's what we're going to start with. What are some graphs you should just always have in the back of your head? And the first one you already have, the line y equals x. What does that look like? I already said the one line. Yeah, it's a line. I guess you need to know its intercept. Where is its y-intercept? Well, origin. And its slope is 1. So you know what the graph looks like. Graph of y equals x looks something like that. Fair enough. Graph of y equals x squared. What does its graph qualitatively look like? Yeah, like a technical one is parabola, bowl shape. And you can check that. 0 squared is 0, 1 squared is 1, negative 1 squared also 1, 2 squared is 4, it gets steeper. Negative 2 squared is the same. X cubed? Yeah, I mean, to the right it looks qualitatively like a parabola, but like, I guess it grows faster as x gets big. When x is negative, it looks like a parabola, but down. Right, and you can do this again by plugging in some points. 0 cubed is 0, 1 cubed is 1, 2 cubed is already 8, so it's off the page already. Negative 1 cubed is negative 1. Nice. Raising something to the 4th power. Again, looks qualitatively kind of like x squared, but flat or close to the origin, and then it grows fast. Feel pretty good. And in fact, let's just check these against computer-generated graphs, see how these did. This button, there we go. Graph of y equals x. That looked pretty close to what I drew. Yeah, I think it's the one that's going to look the closest to right. X squared, that seemed close enough. X cubed. X to the 4th. And now let's just continue a pattern. X to the 5th. Looks kind of like x cubed, but maybe flat or close to the origin, steep or farther away. X to the 6th. Again, looks kind of like x squared or x to the 4th. X to the 7th. So let's notice just some things about this. Based on those graphs, could you classify these things as being even or odd functions? Yeah. Y equals x, even or odd? Odd. Right. I can reflect that over the origin and I get the same line. X cubed, even or odd? Odd. In fact, remember the graphs that I just showed up on Desmos? For absolutely any odd power, did they look odd? Yeah, and that makes sense, right? If you take a negative and do it an odd number of times, you can cancel a bunch more and you're left with one negative sign. Yeah, that should be odd. What about the even power functions? Even or odd? Even. They're symmetric over the y-axis. Okay. And in fact, that's the motivation for using the word even to describe what we use it to describe, and odd to use it for what we just use it to describe. Even functions have the same symmetry as even power functions. Odd functions have the same symmetry as odd power functions. Tell me about the intercepts of these things. Where do they cross the x-axis? Well, you can just see it, right? At 0, 0. Is it the same no matter which one I take? All right. And notice I just said intercepts. I didn't say x-intercepts or y-intercepts because does it matter in this case? No. Where are these things decreasing? And let's still go left to right. Look at those odd power functions. Where would you say those things are decreasing? Are they ever decreasing?
Yes.
There. So remember, decreasing means as the x values go up, the y values go down. So, right, like, there's an x value. As the x values go up, those y values seem to be going up. So I would say these look like they're never decreasing. What about the even power functions? Is there any place where those have negative slope? Where?
When x is less than 0.
When x is less than 0. And in fact, Gesundheit, because of the way that I would describe what it means to be increasing or decreasing, I would say they're decreasing all the way to 0 inclusive. And basically that's just because if you saw that much of the graph, including x equals 0, do you say that that just looks like it's decreasing the whole time that you see? Yeah, so I would want to include the endpoint. Where are the odd power functions increasing?
Always.
Always. And I guess the word always is as good a way to describe it as any. I'll use the interval notation. Anyone have any objections to that? Oh, cool. If you use the techniques from calculus to describe increasing or decreasing, you might get upset because starting at x cubed and then x to the 7th and so on, what does it look like the slopiness of these things are starting at, well, at 0, 0? That was long-winded. What does it look like the slope of x cubed is at the origin?
0.
Looks like it's 0. I would still call it increasing, even though it levels out, because it just levels out for a moment. The y values keep going up as you go through the origin. They just slow down a lot. Even power functions, where would you say they're increasing? I guess the places where they're not decreasing. All right, nice. And qualitatively, a thing to note about these power functions is they all look kind of similar. If you group all of these even power functions together, let's put one more in there. Those all kind of qualitatively look similar, right? They all just kind of open upward starting at the origin. Unless you're drawing a fairly high resolution graph by hand, you're not going to visually tell the difference. So I would in fact say qualitatively, all of the functions of the form x to an even number look kind of like y equals x squared. But maybe we'll be a little more specific. Flat or near 0, 0, steeper, away from 0, 0. That seem about believable? Odd power functions. I think those are going to mostly all look like x cubed. With the same caveat. They're flat or close to the origin, steep or farther away. Nice. So there's the first in the pile of just elementary functions whose graphs you should just keep in mind. If you ever see something that that looks like it's built starting with an x to the fourth, you should just remember x to the fourth is upward opening bowl shaped. It's flat off goes to 0, 0, and steep off all the way. Seem pretty alright? Nice. Root functions. And this one will actually kind of justify a little bit. But you do already know. I'm going to put down here. If you were to graph y equals root x, just like qualitatively, what does the graph look like?
Looks like a parabola flipped on its side.
Look like a parabola
Without negatives.
flipped on its side without the negatives. Yeah, I'd say that's about perfect. In fact, that's the way I'll build it. Let's figure out why it should be like a parabola, but flipped on its side and without the negatives. So here's how I'll think about it. If you want to understand something like y equals the square root of x, well, you could rewrite that as like a square equation, right? What would you get if you solve that for x? You could write that as x equals y squared. Yeah. That's what the square root means. With maybe one added constraint. The square root function is always positive. By convention, you just always take the positive choice of a square root. I guess or 0, if x happens to be 0. Oh, neat. That tells you a lot. If you want to just graph x equals y squared, well, you know what the graph of y equals x squared is, so just swap the role of x and y. So this point at 0, 0, when you swap x and y, will still be 0, 0. That point at 1, 1 will still be 1, 1. Negative 1, 1 will become 1, negative 1. So that pink graph there is the graph of x equals y squared. But you notice, of course, that's not the graph of an equation. That's where this condition kicks in. Y has to be bigger than or equal to 0, so let's just throw out the part of the graph where y is not bigger than or equal to 0. And there, we get the graph of y equals root x. That feel pretty good? Do you think we could do this for all the other power functions too? I think just about. Let's see how things change. So, without using a calculator, let's try to get an idea of the graph of y equals the cube root of x by doing the same sort of thing. So y equals cube root of x. Is that something you could now just solve to get x as a function of y? What do you get? X equals y cubed, I guess? Oh, neat. So that means that this graph should look an awful lot like y equals x cubed, which let's just remember the graph. Qualitatively, something like that. The graph should look like that, but with the x and y coordinates swapped. So 0, 0, still at 0, 0. This stuff in quadrant 1 has y growing much more quickly than x. So now we'll have x growing much more quickly than y, and then the same thing but in quadrant 3. That feel pretty good? Cool. We could say the exact same words and understand like the 4th root or 5th root functions, 7th root, 8th root, 100th root. We could get a graph of all of them. 4th root function, I think, will look qualitatively an awful lot like the square root function. And at the resolution I'm capable of drawing by hand anyway, you can't tell the difference. 5th root function will look qualitatively like the cube root function. Getting a pretty good idea of this? whenever you want, in fact, let's redesign this exercise, this just a bit. If you want an odd root function, take the nth root of x where n is any odd number. Those will all look basically the same as the cube root function, qualitatively. They won't be equal on the nose, right? None of the outputs will actually line up. Well, 3 of them will. Go through 0, 0, 1, 1, negative 1, negative 1. They'll be kind of steep here and then level off. All those graphs will look something like that. Similarly, if you wanted the graph of any even root function, for the exact same reason as for x squared, the square root function, its graph will look like a distorted version of the square root function. So now you've got more functions that you can just keep in your head. If you have something that's built out of something like the fourth root, you now just know what that graph looks like. All right, so let's just conform some things by checking some words like even or odd. So let's see, we saw that there was an issue for y equals an odd root function. Possibly other behavior for y equals an even root of x. All right, so let's start with the question. Are these functions even or odd or nine or both? Odd root function first. So just by taking a look at this graph, does that look like an even function or an odd function or neither? Even? Odd? Cool, yeah, I think so. And in order to check that, pin down the origin, flip it. Does that look like it's still the same function? Yeah, I mean, up to the fact that, like, I didn't do a great job drawing, it was just a sketch. The even root functions. Even, odd, neither, or both. Even? Odd? Neither? Both. Cool. Let's give a quick check. So how can you detect evenness from a graph? A function is even if its graph is symmetric over the y-axis. So let's just check for that. There's the y-axis. Here's a point that's on the graph. If you reflect that over the y-axis, you get that point. Is that still a point on the graph? Is it actually symmetric over the y-axis? Cool. And that was supposed to be like a mild trick question. Like the function really wants to be even. Right? You've got it by undoing an even function. But is the domain of that thing even a domain that's compatible with the idea of being even? Right? Its domain isn't even symmetric over the origin. Let's determine some intercepts. Where do these things have their x-intercepts? Cool. Y-intercepts? Oh, cool. X-intercepts are the same as the y-intercepts, 0, 0. And you can just see that from the graph. Where are they increasing and where are they decreasing? And let's stick with the idea of odd power function first. Take a look at that odd power function. Where would you say that thing is increasing? Is increasing the thing to do first? We're going to do increasing first. Well, let's just give it a quick look.
0 to infinity.
Wait, we're doing increasing?
Increasing,
Oh, 0 to
On.
infinity.
on this one.
Oh,
Let's check. So you suggested 0 to infinity. Yeah, it certainly looks like as the x values go up starting at 0, the y values keep going up. Let's check right there. As the x values go up there, or the y values going up or down?
going up.
They're going up. So I think it's also increasing here. In fact, is there anywhere where this function is not increasing? Oh, cool. Increasing everywhere. Decreasing nowhere. Okay, now the even root functions. So, graph looking something like that. Increasing fast. We did increasing fast previously. Where would you say this thing is increasing?
0 to infinity.
0 to infinity. Can't be any more than that because it's not even defined for x values less than 0. Decreasing everywhere. Nice. So again, like, if you just keep in mind what the graphs of these functions look like, those answers were basically automatic, right? As long as you took a moment to think what symmetry actually detects evenness, you get it automatic. Last one, absolute value function. I think we haven't manually graphed this in the past, but I don't know, let's just ask this fast. What does the graph of absolute value look like? Yeah, let's see, it's on one of these. Yeah, like a V shape. And let's actually see this by using this piecewise description. Absolute value of x is given by x if x is bigger than 0, 0 if x is equal to 0, negative x if x is less than 0. We have a strategy then. How do you graph a piecewise function? You graph each piece, then you put you decide where you need each piece of the graph. So let's graph each piece one at a time. I'll color code here. And then we'll take these pieces and use them to graph the whole function. So one piece at a time. Y equals x. We know what that graph looks like. Straight line, slope 1, the intercepted 0, 0. According to these instructions, for what x values do I care about that pink function?
All the ones in the top corner.
Only the ones when x is bigger than 0. So yeah, only the top column. So, you can start there. There's a piece of the absolute value function. And I put an open circle there because that's a strictly bigger than. We'll fill it in a moment, but for now it's an open circle. Negative x. What does its graph look like? Also a straight line. Slope is negative 1. Right, y equals mx plus b. B is 0, but it looks like m is negative 1. And I care about this graph when x is negative. So still an open circle there, goes that way. And now the last piece of the function says that when x is equal to 0, absolute value equals 0. So what y value do I need to fill in when x equals 0? 0, 0. Oh, cool. So I just need to put a solid dot instead of an open circle. That feel pretty okay? Right, and you already knew that's what the graph had to look like, but it's nice to just see it from the point of view of piecewise functions. All right, let's answer some questions. Even or odd? I saw some, I think I saw people mouthing the right thing, but I can't read lips. Well, let's see. Even? Odd? Cool, great. Yeah, it's symmetric over the y-axis, so it's even. Like this is like the prototypical even function. Even means you don't care about a negative sign. Absolute value explicitly forgets negative signs. What's its domain?
Negative infinity to 0, 0, 0, and then 0 to infinity. Is that how you word it?
How about just negative infinity to infinity?
Yep.
Right, to read off the domain, I just need to know what x values are on the graph. And you told me in the first bit that all negative x values are on the graph, 0 as an x value is on the graph, and all positive x values is on the graph. So that's just all of them. You don't need to tell me what individual pieces are used to get that. What's its range? What output values do you see on the graph? Well, how do you get the range from the graph of a function? So range is like output values, so you just need to tell me what y values you see on the graph. So, are these numbers where my pen is at right now in the range? Okay, cool. So I miss everything that's negative. Is y equals 0 in the range?
Yes.
Numbers bigger than 0? Sure looks like. So what's the range?
0 to infinity.
0 on to infinity. Include 0, you will always exclude infinity. All right, where is it increasing, where is it decreasing? To do this, I guess let's just pick a point on the graph. At that point, is the function increasing or decreasing? Is the slope positive or negative?
Negative.
So the thing is decreasing, it looks like for x values from negative infinity up to 0, then it turns around. And then it starts increasing. All right. I think the last thing on the list was x-intercepts and y-intercepts. And again, those are like easy to see, right? X-intercepts of this function? 0, 0. Hits the x-axis at 0, 0. It like bounces off, but that's okay. That counts as an intercept. Y-intercepts. Same, yeah. Neato, cool. So we have kind of this pile of elementary functions that we can now just like internalize, and you know what those graphs look like. What I'd like to start doing now is, now that we have this collection of functions whose graphs you should just know, let's use them to graph new functions. You know what the graph of y equals absolute value, what its graph looks like. So you can probably figure out the graph of y equals what that graph looks like. And that's going to be the goal of what we'll do right now. And I don't know, maybe just like see something. Let's have Desmos sketch a graph of that, and you'll tell me, like, I don't know, how does it compare with just absolute value? I don't know, tell you like really vague things. How does that pulpal graph compare with the absolute value function?
It's upside down.
Upside down? Looks like it's also been shifted a little bit. Maybe it's also been stretched some, but like that's hard to see at this scale. It's not so huge a stretch. Let's see if we can unpackage how these numbers told us that. Yeah.
I'm pretty sure -3 is a stretch factor.
-3 is like a stretch factor. Maybe that it's negative tells you it's a flip factor.
Yes, that is true. Yeah.
Let's list these one at a time.
Okay.
And like, for now, let's forget about that example and just think about one piece at a time. So in fact, let's do something simpler. Let's keep on studying this function. Caps lock. Let's figure out what happens if I just take a function and add a constant to the output value of that function. What do you think that should do? Yeah.
It should move its intercept.
It should move its which intercept? X-intercept or Y?
Y.
Y-intercept, I think that's right. Because right, how do you get the Y-intercept? You plug in X equals 0. If you plug in X equals 0, you'll get whatever f of 0 is, and then you'll add C to it, so it'll let you move up. In fact, I think the same could be said for like all of the Y values. So, I'm going to say this in two ways because the first one's going to be what I just said in once. Adding C to all Y values. But maybe another good way of saying that is you are shifting the graph up by C. And let's just see if that actually happens. There's the absolute value function graphed. Give me a value for C. Just give me a number. 1. Good. Thank you for not picking 0 or negative. Let's also graph y equals the same function, f of x plus c. That look like the same as the absolute value function, just shifted up by 1? Yeah. And in fact, I can change c and it just tells you how far to shift. If c is negative, you just shift down. Neato. That seem good? What if I add a c to the x inside of a function? What does that do? What do you think that should do to a graph? Yeah.
It should change its x-intercepts.
I think the x-intercepts will wind up moving. I think that's reasonable. In fact, like, everything that has to do with an x value will move. Which direction?
Negative. Or the opposite. Right?
Yeah, so there's like, I don't know, I mean, how many people have just already seen something like this and they're pulling from something they remember at some point? Good. Good. So maybe you remember, if it's in the parentheses, it's going to do the exact opposite of what you expect. So you're adding to the x's, so you think, oh, that should probably shift right. You're adding to x. But it does the opposite because it's inside of parentheses. I think it will shift to the left. And instead of trying to convince you of why that should happen right now, let's just see that it happens for this function. So here's this Desmos graph again. Let's graph f of x plus c. Let's go back to c equals 1. Good enough. Does that look like we've shifted the absolute value function slightly to the left? As c grows, we go farther to the left? Oh, neato. So when you add c inside of the parentheses, you in fact subtract that number c from all x values. Said another way, you shift left by c. Feel pretty good? All right, next question. What if I stick a negative sign in front of a function? What should that do to it? So you take a function and you make all of the outputs negative what they used to be. Output values are like the y values on the function, right?
Reflects the x-axis.
Yeah, it'll reflect over the x-axis. All the y values will become negative what they used to be. So let's write that down. Reflecting over the x-axis. And again, let's just see if that actually happens. Does that look like you've just reflected the original graph over the x-axis? And I'm going to change this to a more complicated looking function so the next example is yet less silly. That still look like you've just reflected the graph over the x-axis? Cool. I'm going to make that 5 just so it's falling over. There we go. Still reflected? Nice. So if that's what happens when you multiply the output of a function by -1, what happens when you multiply the input of a function by -1?
Flips over the x-axis, the y-axis.
Yeah, flips it over the other axis. And if you're like me, it's really easy to misstate which axis you mean to reflect over. So I'm going to write it in a second way too. So on the one hand, you reflect over the y-axis. And why do you do it? You do it because you want to multiply all x coordinates by -1. You reflected over the x-axis because you wanted to multiply all y coordinates by -1. Groovy. And again, let's just see if that works. Here's the function that we have. That look like I've reflected over the vertical axis. Nice. All the input values became negative. All right, 2 last moves and then we'll have everything we need to start putting together. Multiply a function by a number, c. What do you think that should do to the graph? Yeah.
That should stretch the y value.
I hear a call for it should stretch the y values. And let's first try to just intuitively make sense. So this rule says I want to take the original output values and multiply them by c. Output values are like y values. So I want to take the y values and multiply them by c. That sounds like a stretch. Let's see if it works out. So I'm going to write that down. We multiply all y values by this number c. This is also a stretch vertically by a factor of c. So one, very analytic, multiply all y values by c. The other one, geometric. I'm doing a stretch. Let's see if it holds up. Let's make that c a little less extreme. So there's when c equals 1. Does this walk? No. As that parameter c grows, does it look like I just stretch by a bigger factor? Cool. Let's see what happens when c is less than 1. So when c is like a half, all the y values get multiplied by a half. So really I'm compressing instead of stretching. But maybe that makes sense. If you stretch by a factor of a half, that's a compression. That seem okay? All right. And now we'll see one more example of doing something to the input values does the opposite of what you expect. What happens if I multiply the x in a formula for a function by a number c?
It compresses the x value.
I hear a compress the x values. Let's see if it works out. F of c times x. And again, we'll start with c equal to 2. That look like all the x values have gotten compressed. And as that parameter c, let's let it go up to like 10. As that parameter c grows, it gets compressed more and more. Once that c is at 1, it doesn't do anything. When c's are less than 1, it's actually stretching. And I guess that makes sense. If I say I'm compressing by a factor of a half, then you have to like meditate on what that even means. But yeah, that should mean a stretch by a factor of 2. So let's write that down. So if you want to multiply an x by c inside of the parentheses, that means I want to divide all x values on the graph by c. And that is because I want to compress horizontally by a factor of c. Groovy.
Can you say shrink instead of compression?
Yeah, there's nothing magic about the WODs that I picked.
Okay.
Right, if you say shrink and I expect the WOD compressed, that's fine. All right, so let's use this to do some things. So I think we've done a lot of those just visually anyway. So let's actually head down here and see about going through one example of putting a bunch of these transformations together. So let's suppose you want to sketch the graph of 2 times the square root of x minus 2 plus 1. So I want to start with the square root function. Let's see how to do that using these transformations. So basically what I'm going to do is apply every one of the rules at the top of the page one at a time. Starting with y equals the square root function, because this function is built out of the square root function. So, start with that. What does the graph of the square root x look like? And I think this kind of suffers from the like a picture is walk the great many worlds. How do you describe the square root function? I don't know, it looks like a parabola but on its sides, and then you erase the bottom half. But in the meantime, you could have just drawn a picture, right? So, start with the graph of the square root function. Ooh, maybe I'll do one like silly thing. At the origin 0, 0, should I draw an open circle or a solid dot? Open circle? Solid dot? Cool, yeah, I want to include 0, 0. As is, you can't tell if 0, 0 is included or not. Put a solid dot there to effectively communicate that I do mean 0, 0 is included. So here's what I'm going to do. There's the function that I'd like to get. I am going to apply transformations corresponding to each of those moves one at a time, and in a particular order. So first, let's deal with this too. So let's get the graph of y equals 2 times the square root of x. What do you do to the xy coordinates to multiply the function by 2? Vertical stretch by a factor of 2. So since the square root function has this point at 1, 1 on it, the new one will have a point at 1, 2. Otherwise, the graph will look like the same-ish. vertical stretch by a factor of 2. Feel pretty good? All right. Next thing that I'll deal with is this minus 2. So if I want to go next to the graph of y equals 2 times the square root of x minus 2, what does that minus 2 do to the graph?
Your x-intercept over to the right too.
Yeah, and not just the x-intercept. I move everything to the right by 2. Because, right, I want to move it to the left by negative 2. What does it mean to go to the left by negative 2? It means go right by 2. So this point right here that used to be at 0, 0, where will it go? Yeah, that one. 2, 0. Same as you were going to say? Awesome. And I guess I emphasize this point at 1, 2. Where will it go? 3, 2. Add 2 to all the x-coordinates. Otherwise, the graph will look qualitatively the same, and I guess this graph is in orange, so I should go ahead. So I should be consistent with my colors. All right. Last thing to deal with is this plus 1. What does that plus 1 do to the graph of the function?
Lose everything at 1.
Nice. Oh, and the time is even like pretty good. I'm finishing this example like on the nose. Feel pretty okay? Now we've got time to do like a few things with this graph, but not enough time to start another example. So let's see what we can read out from this graph and see if it sounds acceptable. By looking at this graph, what does it look like the domain of this function is? I hear a 2 to infinity. By looking at the graph. Now let's look at the formula. So forget about the graph. If you saw this formula, could you compute the domain? Yeah. It looks like the only thing that restricts it is the square root. Because there's a square root, the thing under the square root needs to be non-negative. Oh, bigger than or equal to 0. Does that correspond to 2 to infinity? Nice. Then I'm happy. So, what will we do next time? We've got these rules, these transformations. We'll talk about why you should apply these transformations in a particular order. Why, if you don't, you'll do something kind of weird. And we'll go from there. We'll use these to do some things. Alright. I have an office hour at 1. I'll have some people dropping by my office at various times, so you can try to find me at points during the day. Take a look at the open-ended and WebWork homeworks. Decide if you have any questions.
So, I have stick fig in this class, and I'm not struggling with that in a sense. So if you have 30, so 3 is the only valuable stick fig number. If it's 30.00, the only.
Oh, significant figures.
Yes.
Oh,
Is that not
okay.
the same thing?
Okay, I caught stick fig. Yeah, yes. You said sig fig, which is a reasonable abbreviation, but I caught stick fig, and I was really confused.
Okay. Yeah. Sorry.
Yeah. So usually, so in terms of effective communication, if you're communicating how many significant digits you have, you can just say what your error bounds are. You can say the answer is 30 within an accuracy of 10. That'll capture it. Well, within an accuracy of plus or minus 5.
Okay.
If you say 30 and then like explicitly put the decimal point, you're telling the reader that I know that that 0 is correct. in the context of this class, what I'll be, if I tell you how to round specifically, then round to that precision. If I tell you I want your answer to be at least this precise, then as long as you include at least that much precision. So I'm not going to be so concerned with those like significant figures in this class. In like a science or engineering class, they're more important because it's part of how you communicate your accuracy. But you can also just like explicitly say that this is my answer with error bounds in this.
Okay.
Yeah.
Thank you.
That kind of clear on the
Yes.
question?
Yes.
Okay, cool.
Thank you.
Yeah.
For the open things, I think it's a great question. It's asking, I don't know if you want us to kind of drawn out.
I designed it a while ago, so like, what does it ask?
It's just showing another way not
Oh, yeah, a graph would do. Yeah, I remember the question. Yeah. No, like. Oh, no, Oh, okay, yeah, that makes sense. Yeah, scroll down and show me. Oh, in fact, like, I said you were missing parentheses, but that parentheses isn't where I mean it. I mean, like, you need parentheses to say that everything inside of the square root.
Because when I look at the comments, I like.
That reads like I'm saying you skipped it entirely. Like, this looks like part 1, which I was happy to like, scroll down and back to that 2. Okay, cool, let's get to it. Oh, okay, so like, it looks like you just skipped that one. Yeah, and it was like the easiest one, like plug into equals 1, see what you get. Yeah, and, well, not with the 5. Because you don't want to send equal 5. Yes. So that's the formula that tells you the distance at any input. Plug into equals 1. Yeah.
All of your office hours happen to line up with so are there any other times
As demand by appointment. What do you want to talk today? Okay. I have class during this next hour. Then from 10 to 11, I'm theoretically free. During the noon hour, I can be free, but I like to be late. So like, you'll have to set, if you want to meet during outside of office hours, just shoot me an email. Today, I can make 11 o'clock. Nope, 10 to 11 walk. Noon walk theoretically, the 1 o'clock hour walk, or the 3 o'clock hour walk. Just shoot me an email and I'll make sure to be in my office. At a glance, do any of those times work for you? Okay, I'll be in my office. Yeah. Hello. Sure. Yeah, I'll be there. Yeah.
Thank you.
Yeah. There's also time like right now. What sort of questions do you want to ask about? Oh, yeah. Okay. Yeah, then it's 10 o'clock.
Sounds great. Thank
Yeah.
you.
Ooh.